Today we're going to talk about mathematical induction, which is a new type of proof format for us. And we use induction when we have a bunch of different mathematical statements, which I'm going to represent here as dominoes. And each one of these statements will correspond to some index. And so it'll be easiest to think about this as being indexed by just the positive integers, 1, 2, 3, 4, 5, 6, and so on. And so, in other words, I'm just saying that this is some statement that involves n equals 1. And this is some statement that involves n equals 2, and so on forever. And now we have to figure out a way of proving all of the statements simultaneously, which sounds like it might be annoying, but one strategy to use is first to prove that this very first statement is true. And so that'll be called the base case in an induction proof. And then we're going to do a bit of an aside, which is we'll show that if you have any two statements, which can maybe be labeled by k and k plus 1, then as long as the kth statement is true, it implies that the k plus first statement is true. And so this part here will be called the inductive step. And so if we go back to my original set of dominoes then, as soon as I've proved that the first statement is true, then I can use whatever I showed in the inductive step to imply then that the second statement must be true. And then if the second statement is true, I can reuse the green part of my proof again to show the third statement must be true. And if the third is true, then the green part says the fourth is true. And these arrows just go on forever. And so then by having proved the first one and then the green part of this proof, I'll have shown that all of the statements must be true. Okay, so an inductive proof really does have the structure of these two distinct parts. The first one's the base case, and the second part is the inductive step that sort of corresponds to the dominoes toppling the next ones over. Let's look at a couple examples, and it will become clearer what the structure of these proofs is. And so let's prove, first of all, that the sum from k equals 1 to n of k is equal to n times n plus 1 over 2. On the very first day of class, you saw several different proofs of this statement, and now this will finally be one more proof of this statement using induction. And so when we write a proof by induction, I typically do start it by just writing the two words that the proof is by induction. And then we're going to have the base case of this proof. And so the base case will be when I plug in the smallest possible n value for which I want the statement to be true. And so for here, because n is in the positive integers, the smallest n value will be n equals 1. And now I have to check that for n equals 1, the left-hand side and the right-hand side of the equation I'm trying to show are actually equal to each other. It is really important that you actually make it clear that you're verifying that the left-hand side is equal to the right-hand side instead of just plugging in numbers without making it clear. And so in other words, I'm going to suggest that you explicitly write out that you're showing that the left-hand side when n equals 1 is equal to the sum from k equals 1 to 1 of k, which in this case is just equal to 1. And the right-hand side is equal to a 1 times a 1 plus 1 over 2, which simplifies again to 1. And so in this case, the left-hand side is equal to the right-hand side, and I'm done. And so a lot of students end up writing that 1 is equal to 1 without having written any of this other notation here, and then it's impossible to see what you actually checked in the base case. And so make sure that it is clear when you're writing your proofs that you actually are checking that the left-hand side and the right-hand side give you the same number when you plug in the lowest possible n value. All right. Now we're done with the base case because we showed that this formula is true for the smallest possible n value, and now we have to move on to the inductive step. And so for the inductive step, what we're going to do is assume the statement is true for n. And so that would be the statement exactly as written. All right, and so this assumption right here has a name. It's called the inductive hypothesis. All right, and so now that we've assumed that, I can write out what we want to show. And we want to show that the statement is now true for n plus 1. And so I'm going to replace the n's everywhere in the original statement with n plus 1's. All right, and so this would be that domino effect right here, where we're assuming that the nth statement is true, and then we want to prove the n plus first statement is true. And since n here is an arbitrary integer, it'll work if I plug in any specific value. And so it works if I plug in n equals 1, now I know the statement is true for n equals 2. If I plug in n equals 2, I know it's true for n equals 3, and so on. And so now, in order to show this statement for n plus 1 must be true, the idea is going to be to find a way of rewriting the sum from k equals 1 to n plus 1 of k, so that the sum from k equals 1 to n appears somewhere explicitly. So first I'm going to write this out long form. So this is 1 plus 2 plus 3 plus blah, 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 plus n plus 1. And so really what I could do is write it a little bit better so that I can see how I could use this assumption more explicitly. And so in other words, all I need to do is make sure that I actually write the second to last term in this sum. And so really it's the sum from 1 to n and then plus an n plus 1. All right, and now our inductive hypothesis told us exactly what this part of the sum should be. And so this is equal to n times n plus 1 over 2 by the inductive hypothesis. And then I still have that plus n plus 1 left over at the end. And so now I just have to do a little bit of tidying. And so I'm going to have to find a common denominator, and I am also going to have to expand the numerator in the first term. And so that's an n squared plus n, in the first term. And then I get a plus a 2n plus 2 when I put everything over 2. And so if I simplify that, that's n squared plus 3n plus 2 over 2. And now I just need to factor it. And so that's an n plus 1 times an n plus 2 over 2. And so if I backtrack a little bit, I can see that that does correspond to the part that I was trying to show right here. And so I am done at this point. The inductive step has been shown, and so the overall proof is done. All right, let's look at one more example of a proof by induction. And so this one's a little bit different because we're trying to prove an inequality. And roughly speaking, we're trying to show that factorials grow faster than exponentials. And so in order to prove this, again, it'll be by induction. And again, I'm going to want to separate out explicitly the base case and the inductive step. And so the base case here is the smallest n value. And so in this case, I want that to be n equals 5. And so here, the left-hand side is equal to 2 to the 5th, which is 2, 4, 8, 16, 32. And then the right-hand side is equal to 5 factorial, which is 5 times 4 times 3 times 2 times 1, which is 20 times 3 is 60 times 2 is 120. And so in this case, the left-hand side is less than or equal to right-hand side, which is what I wanted to show. All right, and so now we can do the inductive step. And so this time I'm not going to write quite as many words, but I can assume that the statement is true for n. And so that's that 2 to the n is less than or equal to n factorial. And then I want to show that 2 to the n plus 1 is less than or equal to n plus 1 factorial. Okay, so I'm going to start again with the left-hand side of what I want to show, and then I'm going to try and relate it back to my inductive hypothesis and see what I can use there. Right, so here, 2 to the n plus 1, that's really just 2 times 2 to the n. And now that I have this 2 to the n explicitly written here, I can substitute in my inductive hypothesis. And so that would be 2 times an n factorial. And so this is by the inductive hypothesis, and you should denote when you're using the inductive hypothesis in your proof. And so now my goal overall was to show that this was less than or equal to n plus 1 factorial. And so I have to somehow connect 2 times n factorial to being less than or equal to n plus 1 factorial. And the way I can do that is by saying that this is less than or equal to n plus 1 times n factorial. And in this case, I need to know how big n is. And so this would have been true as long as n was greater than or equal to 1. But in this problem, we were assuming that n was greater than or equal to 5. And so we're good to go for this line. And then that does connect the last dot here, and so we're done with the proof.